This video is going to go over VSEPR theory, VSEPR. It's going to talk about what exactly this is, why is it important, and then if you are looking at a Lewis structure, well, how do you figure out what the molecular geometry of it is? So let's get started. First of all, VSEPR, that is an acronym, and it stands for Valence Shell Electron Pair Repulsion. So let's walk through that. So valence shell electrons. So we just have valence electrons. We're looking at the electrons in the outer part of the atom, like the ones you draw in the Lewis dot diagrams. And then as electrons are in pairs, which we know as lone pairs, it causes this repulsion. So just like how opposites attract, same things repel, and electrons all have a negative charge, and they will repel each other. So that is how electrons cause these different geometries. These electrons are repulsed by each other because they have the same charge. So electrons carry the same charge, and the charge they have is negative. And the negative charges, because they're the same, they repel each other. So it's sort of like you're trying to bring two ends of a magnet together that are the same. It won't work. And the reason this is important is because the shape of a molecule helps determine its function. And beyond that, where the lone pairs are on the molecule, that will determine some of the properties of this molecule as well. How volatile is it? How stable is it as well? So to give you an idea in terms of these electrons repulsing each other, let's take a look at this simulation. So this simulation, we are looking at the molecule BF3. You can see that in the top right corner. And so as we try to move this around, you can see how it rebounds back into a particular shape. And that's because the electrons don't want to be next to each other because they have the same charge. So they will rebound to a particular shape. And the shape also comes with a certain bond angle. So I can try to move that bond angle, but it'll always settle back out. A shape that you are familiar with, you've drawn the Lewis structure for multiple times, is CH4. And probably just by looking at this, you're thinking, that doesn't look exactly the same as what I've been drawing. And of course it doesn't, right? This is a three-dimensional model, and what you've been drawing is a two-dimensional model. But it's all still here. We see carbon in the center, and that's a bit darker gray, and then hydrogen is going around it. And when you draw it, you have carbon in the center with 4 hydrogens. Well, this one still has 4 hydrogens. Now we just have a particular bond angle, and we have a particular type of shape. This shape is called a tetrahedral shape. All of our bond angles settle back out at 109.5. So no matter how we try to manipulate the bonds, the electrons are repulsed by each other and they'll stay at 109.5. And the reason that our molecules will stay at that certain place is because of electrons. So here's a model of water. So when you draw it, your lone pairs are right next to oxygen, and here we're showing that they have their own cloud that they're in. We can try to move those around, but because the electrons are repulsed by each other, no matter how you try to get them to go next to each other, they will not. Here's another one that you're familiar with drawing, and it's NH3. NH3, N is in the center, it's blue, and then we have 3 hydrogens around it. And you might be thinking, well, what about that lone pair on nitrogen? Here's our lone pair. So all of these turn into particular shapes because of how the electrons are arranged. And that's what VSEPR theory is. We're looking at how these valence electrons are repelling each other and what type of shape that makes. And we can predict the shape and then the bond angles that the molecule will settle out at. So let's go back to our notes. So let's talk about how to figure this out. How do we determine the geometry when we don't have a 3D model, we just have our Lewis structures? Well, the very first thing that you have to do is you have to draw the Lewis structure. And after you have the Lewis structure drawn, then we need to do some counting. We're going to need to count electron groups, bonding groups, and lone pairs around the central atom. So right now, you are probably only familiar with and comfortable counting lone pairs around the central atom. So we need to talk about then bonding groups and electron groups and how to do that. And we're going to do that with an example. Let's choose one that you're already comfortable with, which is NH3. So here's NH3. Let's count up our electron groups first. So an electron group, that could be a lone pair or a bond around the central atom. So that's a lone pair or a bond around the central atom. So in this case, there's 1, 2, 3, 4 electron groups around our central atom. So this one would have 4. Next, we have bonding groups, and bonding groups are exactly what they sound like. So how many bonds are coming off of that central atom? Now here's the thing though, double bonds and triple bonds only count as one bonding group. So for this one, we have 1, 2, 3 bonding groups around nitrogen. And lastly, our lone pairs, we only have 1 lone pair on nitrogen, so just 1. Based upon these 3 pieces of information, we can figure out what type of geometry we have, and we then match it to the chart. So let's fill out this chart, and then as we come across NH3, we'll come back to this. So this chart, we have 1, 2, 3, 4, 5 different types of geometries that you have to know. This is not an exhaustive list. There are way more than just these 5, but these 5 are a good understanding of how our molecular shapes look. So up first, we're going to look at something that has 2 electron groups, 2 bonding groups, and 0 lone pairs. If you have 2, 2, 0, 2 electron, 2 bonding, 0 lone pairs, you have a shape called linear. An example of linear would be CO2, and you already know how to draw this one. CO2 looks like this. We have carbon in the center, double bond on each side, and then our oxygens have 2 lone pairs each. Now keep in mind that 0 lone pair, that applies to the central atom only. So these are the central atom. And that's the same thing that we had listed above, right? All of these things we count around the central atom. So if we have a shape that's linear, that means the bond angle here to there, that is going to be 180 degrees. Just like in math, if something is linear, it's 180 degrees, a straight line. Same thing here. So from that double bond to the other one, 180 degrees. Let's move on to the next shape. The next shape has 3 electron groups, 3 bonding groups, and it also has 0 lone pairs. And this shape is called trigonal planar. An example of trigonal planar is BF3. BF3, when we draw it normally, I'm going to draw this off to the side. Normally when we draw BF3, it would probably look something like this. And that's perfect. That's a great Lewis structure. We're going to draw it slightly different though, so that we show the correct bond angles. So what happens is this angle is actually more to the side, and we're going to make this more even. So if we draw BF3 with the correct VSEPR theory, we could still have that fluorine up to the top, but then these 2 are going to come out to the side. And I know it's hard to draw the Lewis structures in these teeny tiny boxes, but we'll give it a go. So it would look like this. And each of the bond angles here are 120 degrees. So this angle is 120 degrees, and then so would this angle and that one. Those will all be 120. So trigonal planar as a shape is 120 degrees. Up next, after trigonal planar, we have something called bent. A great example of this is water. Normally when we draw water, we've drawn it like this, and that is really great for the overall shape of it. The only thing that we're going to do is we're going to just angle it differently. So we're going to take this whole thing and rotate it just to show the angles a little bit better. So we're going to draw it like this. That just helps us see our bond angles better. And the bond angle of water, we are looking at 109, well, slightly less than 109.5 degrees. Now let's fill in those electron and bonding groups. So from here, electron groups, we have 1, 2, 3, 4 different electron groups. Only 2 of those groups are bonding though, 1 and 2. Those are the only ones that are bonding. And then we have 2 lone pairs on oxygen. So something with 4 electron groups, 2 bonding groups, and 2 lone pairs, that gives us a bent shape with an angle of slightly less than 109.5. Our next one is called tetrahedral. An example of tetrahedral is CH4. You guys know the prefix tetra means 4. So a lot of times if you see something with 4, you might be looking at something that's tetrahedral, but it is best to double check. So CH4, when we typically draw, it looks like this. From this 2D model, these look like 90 degrees. However, that's not what actually occurs in real life. In 3 dimensions, we can see that this shape is a little bit different. So it's not exactly at 90 degrees. In fact, this is 109.5 degrees. And we can see then, you can imagine it sitting on top of a table, and we've got that pyramid shape underneath it and one coming above it. So this is our tetrahedral shape. Let's draw it more like the 3-dimensional model for our Lewis structure so that we can better visualize it. So in order to do that, we still have carbon in the center and a hydrogen coming off the top. But then we had 3 of them below. And that just gives us a better visual. We said all of these were 109.5 degrees exactly. So we have 109.5 degrees. Let's go back and look at our electron and bonding groups. Off of carbon, we have 1, 2, 3, 4 electron groups. All 4 of those are bonding, and there are no lone pairs. So we see this 4 and 4 and this tetrahedral shape. Our last one that you need to know, and if you remember back, we had an example that we have not yet figured out. NH3 is going to be an example of our last type of shape. Our last shape is called trigonal pyramidal. So just like how we had NH3 up here at the top, that is going to be our example for this one, NH3. So NH3 in the 3D model, though, is a little bit different. We don't see these 90-degree angles coming out here. We really see is this, pyramid shape underneath it, which is where it gets its name, pyramidal. And then trigonal, we've got 3 bonding groups off of nitrogen. So this is what trigonal pyramidal actually looks like. Let's try to draw it more similar to that 3-dimensional rendering. So we have N, and then our 3 H's coming off of it with our lone pair here. So we know that this lone pair up at the top is really pushing down those other bonding groups. The angle that we see for this one is the same as our bent, slightly less than 109.5 degrees. Electron groups around nitrogen, 1, 2, 3, 4, we've already done that, listed those above. Bonding groups, there's 3, and we have 1 lone pair. So this one, NH3, the molecular geometry is trigonal pyramidal. Before we wrap up these notes, want to talk about then how do we just go from looking at a Lewis structure to matching up what geometry it is. So we're going to try a problem together. We're going to look at H2S for our example. So the first thing that we need to do, as we're following our instructions on this page, is to draw the Lewis structure. Then we're going to count the electron groups, bonding groups, lone pairs, and match to the chart. So let's draw the Lewis structure first. We have 2 hydrogens. They each have 1 valence electron. Sulfur has 6, and our Lewis structure ends up looking like this. It's okay that it's not drawn in the correct geometry yet. This is a fine 2-dimensional model. So we need to count our electron groups. Electron groups, we have 1, 2, 3, 4. Next, we need to count the bonding groups. Bonding groups, we only have 2. Last thing, lone pairs on the central atom. We see 2 lone pairs, so we have 2. The last step of the instructions says to just match it to the chart. So we're going to match the numbers 4, 2, 2 to the chart. 4, 2, 2 is right here. That means our configuration for H2S is bent. Because we now know the type of configuration it is, the shape is bent. We also know the bond angle, and the bond angle on the chart says it is less than 109.5. Okay, so quick recap. VSEPR theory, valence shell electron pair repulsion. Because of the presence of valence electrons, and especially the lone pairs, we get these certain shapes that emerge because the electrons don't want to be next to each other. It's very important to know the shape of a molecule. That helps determine its function and how it behaves with other molecules. To figure out the geometry, draw the Lewis structure, and then we need to count electron groups, bonding groups, and lone pairs, and then we match it to the chart. And we can then figure out the name of the geometry here in the center. Okay, that is it for VSEPR theory notes.